Hi folks, we are on Unit 4, Day 4, and in today's lesson we're going to be looking at some graphical limits, and in particular limits of composite functions from a graph. So instead of analyzing these algebraically, this is going to take a look and sort of test your ability to understand what the limit is talking about from a graph, and not just from an individual graph, but when we have a composition of functions. So I am going to put a link in your outline for composite functions. So that was, you guys would have looked at that in grade 11 and 12, where you would do, for instance, f at g at x. So it's a function within a function. If you are a little fuzzy on that, please go back and watch the link from the advanced functions work when you were dealing with that, just as a bit of a review before you do this lesson. Okay, so for the first one here, we want to find the limit as x approaches 0 of 2 times g at x. So here, this function here, this blue one above, is a graph of g at x. So we're going to take a look at what that would mean. And remember, for a limit to exist, we would have to have both the left side and the right side being equal. So if we look at 2 times the function g at x, remember that would be a vertical stretch by 2. The limit as x approaches 0 from the left of 2 times g at x. Wow, lots of brackets there. I shouldn't have included one of those. Here we're looking at this side of the function, and even with a stretch of 2, that's going to increase the height here. So it would approach a value of 2. So that would equal 2. If we were looking at the right-sided limit, the limit as x approaches 0 from the right of 2 g at x. So here, this would be a stretch factor of 2. Here, we would approach double this height, so we would be approaching 6. So since the sided limits are not equal, then that means that it does not exist. So you should just put D and E for does not exist. If these two sided limits were the same, then we could establish a value for that limit. Okay. So here, if the function's continuous, remember that we can separate that this would be the limit as, this is a little faint here, that is actually a -3. I'm not sure if you can see that in the video, or maybe I made it worse with my marker there. But here we have two graphs. We have a graph of h at x and a graph of g at x. And if we have continuous functions or limits that exist, we could say that the limit as x approaches -3 of h at x plus g at x, so combining those two functions, is the limit as x approaches -3 of h at x plus, remember our limit properties here, the limit as x approaches -3 of g at x. So the limit as x is approaching -3, remember we're tracing along the path of the function towards -3. We don't care that the actual value of h at -3 is actually 0. We care about what the function's doing right around -3. So as x gets closer to -3, the y value of this function h at x gets closer to 3. So that's equal to 3. Similarly, we could look along the function g as we get closer and closer to x equals -3, the g at x function gets closer and closer to 2. So we just kind of analyze those individually, and remember our limit properties that we can find. If we can find the limit of one and the limit of the other, we can just add those two limits up. So that's a 5. Similar kind here, but this is going to be a little bit more complicated, because here we would be looking and saying, okay, the limit as x approaches -2, again, I think that negative is very faint, but I'll maybe darken it up a little bit to make sure you guys can see it on the video. That's a -2 So the limit as x approaches negative 2 of g at x plus h at x. So if we look here and we trace along g at x going towards negative 2, I get two different values from the left and from the right. You would say, oh, well, I don't have a limit that exists here, because if I'm tracing along from the left, I get a value of 1, and if I'm tracing that along this from the right, I get a value of 4. So the limit as x approaches negative 2 of g at x does not exist. And you'll see that that's actually the same for the h at x function, but that doesn't mean that the limit doesn't exist overall. We're going to have to look at the separate limits. So we can say for sure, yes, the limit as x approaches negative 2 of g at x does not exist, and the limit as x approaches negative 2 of h at x does not exist. But that doesn't mean that the limit of the sum of their two functions doesn't exist at negative 2. So we're going to analyze that a little bit more. So here, what if we looked at the left-sided limits for g at x plus h at x? So let's evaluate the limit as x approaches negative 2 from the left of g at x plus h at x. So we could say that that is the limit as x approaches negative 2 from the left of g at x plus the limit as x approaches negative 2 from the left of h at x. Remember our limit properties, we can divide those up. And we can evaluate these sided limits. The limit as x approaches negative 2 from the left, so coming from the negative side of g, we get a limit of 1 for just the sided limit. And for h at x, as we approach from the left-hand side, so from the negative half, we're going to get a value of 4. So that's equal to 5. Now what happens if I do the right-sided limit? So here, I would do the limit as x approaches negative 2 from the right of g at x plus h at x. And maybe you're kind of taking a look and saying, ooh, this might work. We'd have the limit as x approached negative 2 from the right of g at x plus the limit as x approached negative 2 from the right of h at x. Now g at x, if we're approaching negative 2 from the right-hand side, from the positive value, we get an answer of 4. And on h at x, if we're approaching from the right, from positive or bigger numbers, we get a value of 1. But that's also equal to 5. So, because the limit as x approached to negative 2 from the left of g at x plus h at x, that equals the limit as x approached negative 2 from the right of g at x plus h at x, then that means that the limit, just as x approaches negative 2, because the sided limits are equal, that means that this value of 5 is the limit. So the limit as x approaches negative 2 just overall, not from the right or the left, of g at x plus h at x equals 5. So even though their individual limits might not exist, it is possible to have the sum of the two functions. That limit may actually exist. So same kind of idea here. We have two functions, h and g, and we're looking at the limit as x approaches 3 of h at x times g at x. So you can see here, these are discontinuous functions at 3, and quite clearly the limit as x approaches 3 of h at x does not exist, and the limit as x approaches 3 of g at x does not exist. So we know that for sure. So the limit as x approaches 3 of h at x does not exist, and the limit as x approaches 3 of g at x does not exist. We don't necessarily have to write that down as part of our solution, but I wanted to just clarify, like, that limit doesn't exist. If you said, what's this function doing as x approaches 3? We don't know, because you have to say which side. And then same with here. But we may be able to actually get a value. So we're going to do that same thing with the two-sided limits. So I'm going to say that this would be, I'm going to look at the limit of the product of those two individually from each side. So I'm going to take the limit as x approaches 3 from the left of the product of h at x times g at x. Okay, so here we could say that that's the limit as x approaches 3 from the left. Remember, this is my limit laws, the rules that we can use to evaluate limits, that I can break these up and evaluate the limit of h at x as x approaches 3 from the left and the limit of g at x. And if I'm only looking at the left-sided limits, the limit of h is going towards 1 and the limit of g is going towards 5 from the left side. So we can multiply those two limits, those two values, and we get a value of 5. We can do the same thing with the right-sided limit. So the limit as x approaches 3 from the right of h at x times g at x, that's going to be equal to the two individual limits multiplied together. So the limit as x approaches 3 from the right of h at x times the limit as x approaches 3 from the right of g at x. Okay, so now we're going to look at our right-sided limits. For the function h, as I'm approaching from the right-hand side, I'm going closer to 5. So that's a 5, just kind of by inspection from the graph. And then on the function of g, if I'm looking at the graph of g, I'm going closer and closer to a y value of 1. And you can see, just like the last example, we do end up with the same value. So we'd say, since the limit as x approaches 3 from the left of h at x times g at x equals the limit as x approaches 3 from the right of that same product function, then we know the limit as x approaches 3 of h at x times g at x equals 5. So because the two-sided limits are equal, we can evaluate the limit at that point for the product of two functions that happen to have limits that didn't exist at that point individually. So for this one, we have the limit as x approaches -2, again, a really faint negative sign that I'm not sure you guys will be able to see on the video here, as x approaches -2 of g at x over h at x. So we can try just evaluating what's happening here. So this would be the limit as x approaches -2 of g at x, just remembering that you can use your limit laws, and the limit as x approaches -2 of h at x. We do have to make sure that that denominator is non-zero for this to work out, but we should be okay. So if we look as x goes towards -2, we are getting closer and closer to a y value of 5. Again, it doesn't matter that you've got that point down there. We're just talking about what's the function doing as you get close to -2. The fact that it jumps down there and you've got a separate dot and a hole, not not an issue. It just says, what are you going nearer and nearer to? And that's getting close to the value of 5 as x gets close to the -2. So that's a 5. And then in the denominator, as x gets close to -2 here, our y value is getting closer and closer to 1. So that's just a 5. So this one was pretty straightforward. We didn't have to do the sided limits. You do just have to watch out and make sure your denominator is not 0. But you can always break up whether you're working graphically or algebraically using those limit laws that we talked about on, I think, day 2 or 3. Now, we've got another 2 graphs. We've got our G and F. So here we've got 2 functions, and we're looking again for the quotient, and we have the G over F as x approaches 3. So as we're going closer to 3 in the x direction, we see that this is coming to around 3. And here we are going to run into some trouble because as x approaches 3 from either side, here we're approaching 0. And that's the one that's in the denominator. Okay. So we would just say, so we would get 3 over 0, but obviously we can't divide by 0. So here we're going to have to say, because the limit as x approaches 3 of f at x equals 0, the limit as x approaches 3 of g at x over f at x does not exist. So just kind of saying that because we've got our denominator coming to a 0, the limit overall of that rational expression does not exist. Now this is one where we're using composite functions and a little bit of kind of a way that might make you think a little bit more deeply here. So we have 2 functions, again, g and h, and we're looking for the limit as x approaches 3 of g at h at x. So h of x is going to be my inner function, and then I'm going to evaluate the limit of g on that outer function. Okay, so we have to kind of think what this would mean. So we have to evaluate what's happening with the inner function as x approaches 3. Okay, and then that's going to be what the outer function is approaching. So the inside function here, we're going to evaluate as x is getting closer and closer to 3. We have our y value getting closer and closer to 2, right? So the limit as x approaches 3 of h at x equals 2. Now remember, when you learned about composition of functions, we said, oh, okay, the output of the first function becomes the input of the second one. So the y value of the first function becomes like the input value, the x value of the second function. So this 2 is really saying what's happening to the g function as x is getting closer to 2. So now we're going to have to say, kind of transfer this 2 and say we want to now find the limit as x approaches 2 of g at x. So now we're going to look along the g function because this is my output, and then I'm going to use that to analyze what's happening at the g function because the output value here is 2. So now that's g at 2. So the limit as x approaches 2 on the g function is going to be 0. So we have to kind of look at the output of the inside function and use that as the input to the outer function. They do get a little bit tricky, especially sometimes when the sided limits don't exist. So here we have the limit as x approaches 3 of g at f at x. Okay, so we see a discontinuity here at -1. That's okay. But we're not really interested in x approaching 3 on the g function, just my inside function. You have to start by evaluating the inner function. So I'm going to say, what's the limit as x approaches 3 of f at x? And if we look as x gets closer to 3, the y gets closer to -1. So then this output, that y value, becomes the x value when we're evaluating the g at x function. So this is going to be the limit as x approaches -1 of g at x. And that, as x approaches -1, that does not exist. And I'm going to come back to this in a minute, because the next one is going to throw a little bit of a wrench in this works. Because obviously as we're going towards -1, it's discontinuous, and the two-sided limits are not equal. Okay. Now let's take a look at this one. Here we have the limit as x approaches 0 of f at h at x. So here's my f function, here's my h function. Okay, so we want to evaluate the limit as x approaches 0 of the inner function, so of h at x. And we see that the limit as h approaches 0 is going to be -1. So we want to take a look here at the limit. Remember, the output of the inside function becomes the input of the outside function as x approaches -1 of f at x. Now we see we've got a discontinuity here at -1. From the right, it's approaching positive infinity, and from the left, it's approaching negative. Now, I want to kind of analyze what's happening here and think about the sided limits, because sometimes they do matter, and this is probably the trickiest thing to kind of conceptualize, probably in this whole unit, for sure. So I want to take a look here and say the limit, what if I evaluated this as a sided limit? The limit as x approaches 0 from the left of h at x, and the limit as x approaches 0 from the right of h at x. Now I know that these are both equal to -1, right? I'm going towards -1 from the left and towards -1 from the right. But what side of the -1 am I approaching? Here, on this side, I'm approaching the -1 from above, from bigger numbers, right? -0.5, -0.8. These are all numbers above the -1. And that side might matter, because remember that that's now going to be the input over here. That's what goes here. So maybe we're just doing a sided limit. And let's check the other side. I'm approaching 0 from above, and my value, -1, it's going to be -1, but all the numbers are going from above. So it is approaching from above. Or from the positive direction. So what if I take this, because these are equal, because these are both approaching from the positive, I can say, what happens if I approach -1 from the positive side, from numbers that are bigger than -1? Now, if I look at the graph of this function, I can actually answer that. I can say, what happens as x is approaching -1 from numbers that are bigger than -1? It's not either or. It's not two different sides now. It's just this one, just the positive side. And that's going to be positive infinity, which is also not actually a value, but we can distinguish that it's the positive infinity side, not the negative. Now, would that have worked on the last example? I'm going to pull this back. This is the one I just did where I said it doesn't exist. There's no value here, right? So if we had talked about the limit as x approached 3 from the left of f at x, and the limit as x approached 3 from the right of f at x, here, this would have given us, approaching 3 from the left, would have given us a value of -1 from above, right? It's coming down from the higher numbers towards the -1. If we were approaching 3 from the right, we would have gotten still -1, but it would have been approaching from below. Okay, so here, this would be, because these, you do have to consider both, okay? So now, if we were going to evaluate the limit as x approached 3 from the left of g of f at x, that would be the limit as x approached -1 from the right of g at x, which is approaching -1 from the right, we get 0. And then the limit as x approaches 3 from the right of g of f at x would be the limit. And now we've got this side. If we approach the 3 from the right, we get out a -1 from the left, from below of g at x. And then that would have been approaching the -1 on the g function from smaller numbers, from below the -1, and we would have gotten 3. So this, because the sided limits are not equal, it doesn't exist. So it doesn't always work, but sometimes if you analyze which side you're coming from, you can actually get an answer. So the last one, I'm just going to rewrite this bigger. It says, what's the limit as x approaches -1 of f at x? So here, this is one that we're going to kind of take a look at. As the inner function approaches -1, we're coming towards 2. And then the outer function, also the same graph. Now if we're approaching 2, it looks like it's not going to exist. But we're going to analyze those two-sided limits. So if I say the limit as x approaches -1 from the left of f at x, so it's like a composite function of itself, this would be, if we're approaching -1 from the left, we're approaching 2, but we're approaching it from below, from 1.5, 1.8, 1.99. We're coming at that 2 from numbers that are below 2. So this would be the limit as x approaches 2 from below of f at x. Now, if we're approaching the 2 from numbers smaller than it, we get 5. So that's going to be the same from the right. You see how we're approaching the 2 also from below, both from the same side. So here we could say I'm going to evaluate the limit as x approaches -1 from above of this composite function. So the limit, and I didn't break this up this time. Maybe I should have. You guys absolutely can. I'm going to say this is the limit as x. Let's figure this out. If x is approaching -1 from above of the inner function. So we're going closer to -1 from the bigger side. So from stuff over here, we're going to zoom towards 2, but we're coming at it from below. So that's a 2 from the negative side. Now we're working on the outer function, the f at x on the outside. And again, this is going to be approaching 2 from smaller numbers, from the left-hand side. So that's 5. So because the sided limits are equal, we can actually evaluate this even though it looks like it has a discontinuity. So that's everything. The next lesson is going to be on limits of trig functions, which is optional for anybody taking their regular MCV course. But if you were taking the pre-AP, then that is mandatory because that's things that can show up on the AP exam.